Okay, so last time I had to end real quick because the time was up. I mean, we can remember in these 15-minute intervals. I wanted to tell you a little bit about where some of these dikes are here in North Carolina. If you've ever been up to the zoo, the North Carolina Zoo, up in Asheboro, if I remember right. If you go to the bear enclosure, there's this big black kind of almost looks like a wall of rock where the bears are, and that's actually a dike. It's a dike that actually formed when Pangaea was being split apart, and we're on the western side of Pangaea, and then the Africa and Asia is on Europe is on the other side, right? And pulled apart, and so that evidence of that is actually we can see here. We can also see some down to the south of us, down near the sand hills of South Carolina. And so, but anyways, we can see them all up and down the coast here, and they're just these big strips of dark volcanic rocks that went through the other rocks within the region. So another thing that actually can happen is what we call a volcanic neck. Now, a volcanic neck is just the remnants of an old volcano. And here's a great example of this one is Shiprock Peak. And this rock right here that I have in my hand is actually a rock from Shiprock. I got it last summer when I was out there and actually took a sample from this dike that actually came across here, right? And so this came up through the dike and cooled off inside the dike, and then the hard stuff, the plumbing of this basically cooled off, and then the soft stuff around it eroded away, leaving behind this dike, this volcanic neck, which is the remnants of the ancient volcano, the subsurface, and then the plumbing to that area, which is what we call these dikes, right? So there's just some examples of what we call plutons. And remember, plutons are things that cooled off underground. Just like Pluto is the god of the underworld, they cool off underground. Okay, so those are all examples of plutons: volcanic necks, dikes, sills, laccoliths, and batholiths. Right? Those are the examples of plutonic features that you can see here in North Carolina, even. Now, we don't spend a lot of time on plutonic features because they're actually not as exciting as the other portion that we're going to be talking about, which is the volcanic features. Volcanoes have caught lots of people's imagination because you have these big videos about them. They can be dangerous. They can be, and so people enjoy them. They like going and seeing them, and they're beautiful places. And so we need to understand a little bit about them. So this one right here is actually a Hawaiian volcano. This is in Kilauea. Kilauea has actually been erupting actively since the 1980s, early 1980s. And it's been erupting ever since. Now notice a couple of things about the lava coming out of this volcano. First of all, it flows quite well, right? But it also has this really dark color to it. So if it has dark color and it has a low viscosity, which means it can flow really well, what kind of magma or lava did it come from? What's the composition, the chemical composition? And you probably should already know since it says it right down here. It's mafic. And because it's mafic, the gases can escape out of the magma, the lava quite easily. And as it does, the lava can flow very easily as well. It doesn't have a lot of silica in it, so it's not nice and sticky. It's fairly hot, and so it actually flows quite well. It has a low resistance to flow, and therefore we call it a low viscosity. And so mafic eruptions are what we call passive eruptions. They don't explode violently. They're just these lava flows that have very, very small little ash clouds, very, very small, and mostly lava flows. Okay? So, but then there's the other volcanoes. And this is what we call mafic. And remember, we have mafic and then we have felsic, which is at the other end. Well, in between is what we call intermediate, which is then in between the felsic and the mafic and has the intermediate kind of characteristics to it. This is an intermediate eruption. This is Mount St. Helens and Mount Pinatubo in the Philippines are examples of what we call Plinian eruptions, which are often come from intermediate or felsic eruptions. Okay, remember these are the ones that have a lot more silica in them, higher viscosity, and so the gases can't escape. And if the gases can't escape, then that pressure is going to build and build and build until the pressure explodes, in a sense. It's kind of like your pop bottle. And you get your pop bottle, you shake it up, have all those gases in there, right? pull the top, and all the gases explode, right? Because basically you're having going from the gas to the liquid to the fluid, and all the gases want to escape. Same thing happens in a volcanic eruption. All the CO2, the water in the magma wants to escape, and if it can't, the pressure will build and build until it explodes. And these violent or explosive eruptions can be very, very dangerous. Mount St. Helens actually was fairly large, but not as close to Pinatubo. Pinatubo, this is Clark Air Force Base, which is almost 50 miles away from the volcano, and this ash cloud across is about 25 miles in diameter. It's huge, huge ash cloud coming towards Clark Air Force Base. I say this used to be Clark Air Force Base because it's no longer in existence. It was pretty much buried by volcanic ash. They did not rebuild it. That was back in the late early 90s, I think 91 if I remember right. And so, but huge impact on this. And this is just what we call an intermediate eruption. There's so much bigger eruptions than this. This is actually one of the biggest ones we've had in the last 100 years, but it is small relative to other kinds of eruptions. So realize that these can get very, very big, and the ones that we saw from Mount St. Helens is relatively small, and so in cases Pinatubo. So why are these different eruption styles? Well, it comes down to really two different things. It comes down to temperature, gas content, and silica content, which all happen to do with viscosity. So the viscosity and the composition of the material makes it so that it's more explosive. Things that are more resistant to flow can't have the gases escape, therefore it actually will have the built-up gases that explode. Things that actually can let the gases escape, those will form these nice vesicular materials, and the gases are going out, therefore it actually lets the lava flow better. So just as a reminder, which one of these fluids that I have here are more viscous, the honey or the water? Now hopefully you remember that it's the honey, right? If I had a big vat of honey and I tried to walk through it, it'd be kind of tough. If I tried to walk through the water in that same vat, it's going to be a lot easier for me to walk through. Well, let me give you one more example. Which one's more viscous, the air or the water? Both are fluids, because fluids actually flow, and air is a fluid. I know you don't like to call it that, but it flows, and it is a fluid. Okay, so what you usually think of fluid, it also has to be a liquid. Okay, but both of these things are fluids. The honey and the water and air is all fluids. Well, which one's the least viscous amongst those? The one that doesn't flow the most. Well, it's the honey. Well, which one's the most? Sorry, that's the least viscous. Sorry, would be the air, the one that flows the best. Whereas the honey is the one that would flow the worst, right? Which would be your most viscous material. Things that are most viscous, going to not let the gas escape, therefore become explosive. Things that are low, have a low viscosity can let the gas escape. Okay, so if you have, we've talked about Pinatubo and Mount St. Helens, and Mount St. Helens is down here, and they have a conservative estimate of about 0.2325 cubic kilometers of material going up, but some people have suggested it's all the way up to about 1 cubic kilometer of material. So this is how we actually classify volcanic eruptions, based off of how much material is actually exploded out of the eruption. Now, I like to use the upper end value for Mount St. Helens of 1 cubic kilometer, because it makes the math a lot easier. So if I have 1 cubic kilometer, we call that a VEI of 4. That means that volcano is on the scale. This is a logarithmic scale, so it goes up by 10 times each time. So a 5 is 10 times greater than a 4, and so forth down the line. So a 7 would be not 20 times greater, but it would be 100 times greater, 10 times 10, right? And then the 4. And an 8 would be how many times more than a 4? Well, you subtract the 2 and 4. It would be, so it would be 10 times 10 times 10, right? That's 10. And to be able to do that, so that would be, let's see here, that would be 10 to 100 to 1,000 to 10,000, right? Okay, so these are a lot different, okay? Let's say if I had Mount St. Helens versus a Yellowstone eruption. Yellowstone eruptions are about the purest or most felsic eruptions you're ever going to have, and we have not had one in our lifetime. The last one to erupt was 640,000 years ago. Which, by the way, it's overdue. Yellowstone is overdue to erupt. But the problem is the air bar is plus or minus 100,000 years, so we don't really know when it's going to erupt. It could erupt tomorrow. It could erupt in 70,000 years. But it is overdue. And we've had scares before. But we'll talk about that later. The last time it erupted, it had 1,000 cubic kilometers. So that means that it was almost like 1,000 Mount St. Helens going off all at once. Massive, massive eruptions. Okay, but that's not the biggest one. The biggest one that we have is Toba. That was in the Philippines, but it was 2,800 cubic kilometers. That means it's 2,800 times larger than Mount St. Helens. This guy here, what happened about 74,000 years ago, it happened during a time frame when humans were actually, as seen in the fossil record of humans, that all of a sudden they died out. Or not died out completely, but got pretty close to dying out. And part of it is because the ash in the atmosphere from this volcano changed the climate all around the world, and a lot of people have died out because of that. We'll talk more about that later. But the point comes here is these volcanic eruptions can become big and become very, very dangerous. So Mount St. Helens is a good example of one that is a VI of 4. Toba, VI of 8. That's about as large as it gets. Okay. Hawaii, it's been going on for a while. It's a VI of 0. It has lots of lava flows coming out, but the ash clouds are pretty much nothing, and so therefore it's not really that dangerous. And so we call it the volcanic explosivity index is really low. So how bad can this be? How bad can these VAIs be? Well, it depends on where the volcano is and how bad it actually is. If it's near a city where there's lots of people, you're going to have lots of people die, right? Or if it's so large, like a 7 here, where the ash is all over the world, like in Tambora. Tambora had changed climate all around the world. During the United States, notice it's 1815. So we lived here in the United States during the U.S. was around during that time frame, and they actually record snow and frost in Washington D.C. area during July, which means that the crops that year did terrible. They had crop failures for multiple years after Tambora hit. Because that ash went up into the sky and the ash actually blocked out the sunlight around the world, it actually caused everything to be cooler and caused us to, so we didn't have very much food. Because of that, we had starvation around the world because we had crop failures around the world. And so notice that happened in Tambora, but it also happened in Iceland back in 1783. Now, what happened during that time frame, by the way, that was during the Revolutionary War. Benjamin Franklin was actually in Paris when this went off, and he remembers this black cloud of ash, and he says it in his diaries. This black cloud of ash actually going over France and causing starvation because of crop failures all over the area during that time frame. And anyways, so just realize that also that's one of the causes of starvation is or causes of the volcanic hazards is because of the climatic effects that a volcano can have. Other things they can have are like volcanic mud flows, like a lahar, or these big ash clouds, which we call pyroclastic flows. They can be very dangerous. So these can kill people all the way up to 92,000 people, to 23,000 people with a lahar. It's a volcanic mud flow. Or they can be fairly passive, like the Kilauea, where it's had one death since in 1924 because of a falling rock. Basically, somebody got too close to the vent, and it was just basically human stupidity, as it comes down to it. So anyway, so they can be bad. It can be not very bad. It all depends upon lots of different factors. But how viscous it is, or how felsic a magma it is that's coming out, has a huge impact on how explosive the thing will be. Okay, so when you have things coming out of volcanoes, you have basically 3 things coming out of that volcano. You have volcanic gas, lava, or pyroclastics. Now, we've already talked about pyroclastics. Pyroclastics are basically particles of fire, in a sense. So anything ash, or anything that comes out of the volcano. I'll show you some examples of some in a minute. Okay, so here you can see examples of pyroclasts. You can see all this magma coming out and other material, or ash in the distance, all coming out of the volcano. And so these are fire particles. Okay, and then you have lava like this one here, or the gases. Now, if felsic magmas are more viscous due to their composition and temperature, what does this say about the eruption style? This is just a review. If they're more viscous, the gases can't escape. Therefore, the pressure builds up, and therefore they're dangerous, right? So the more felsic magmas are more dangerous, they're more explosive magmas. What magma is at the bottom picture? Just kind of review again. Dark, can flow really well, so has a low viscosity. This is a mafic magma, so therefore has more passive eruptions. Okay, so the gases that can come out, number one gas coming out of a volcano is actually water. Water vapor is a greenhouse gas, though, and it can actually impact climate. But so is carbon dioxide, a greenhouse gas, and it can also impact climate as well. Some people